I've been doing some work with an IDE interface trying to access a CF card, compact flash card. And in this video, I'm just going to walk through some of the things I've been learning or bumping into, I guess, as I go through this. Previously, I've shown a picture that looks like this. This is the PCB that I had ordered up to basically just give me easy access into some of the signals on the ISA bus, along with some decode logic just to make sure I'm only writing back out data to the bus when appropriate and only reading in information into the registers, basically, of my IDE drive when it's appropriate. Along with that, I've got some of these, what you're going to see is just basically headers that give me access to any of the signals on the ISA bus so that I can tap into those easily. And I am buffering the data input-output coming in and out of this card. And then I've got some addressing over here that I can modify at what address, my IDE device or devices will show up as. And when I went into this was maybe the schematic that I had used when I ordered up that PCB. To the left is the, I think, kind of the standard for the pin out of an IDE connector, or at least a 40-pin IDE connector. And many of these signals were new to me. This, CS1 FX, CS3 FX, and there's still some other signals that I'm still working to do something with in the future, especially around DMA. But what I got into as I started actually working with this is that what I had laid out for logic really wasn't going to work. So I ended up modifying it a bit, and what you're going to see is that some of this up here when it comes to connecting to some of these pins that are these CS1 and CS3, kind of these cable select type of signals, that the way I had it set up just wasn't good, and you're going to see that those are going to change. And I'll also mention that this is a reset that I was bringing in a high, and basically for a reset as an active high, and found out later that I needed an active low for this, which was interesting because I was doing a fair amount of troubleshooting just to realize it was active reset the entire time. So that didn't get very far. I was able to find that, I guess, fairly quickly though, but it did slow me down a little bit. So here you can kind of see what the changes look like. So I have kind of reworked some of this logic down here, and I'll post this to a blog post if you just kind of want to look through what my current state is. This still isn't done, but this is as it sits today, and I'm using the ICs that I had on the card. And I know I can consolidate those. Like here, there's absolutely no need for an 8-input NAND gate if I'm only using 2 of the signals. So that, I'll rework that. And then I've got over here some unused pins, and same with maybe getting down here into this OR gate. There's maybe some stuff I'm not using. So I'll see if I can maybe shrink that logic down. But if I come over here, basically now at this point, I'm gonna order an updated PCB at some point. I still have more to learn here before I do that, but essentially I'm just going to have a pair of connectors, and that pair of connectors, I think I'm going to pretty much run through the same pair of buffers here, and have basically a master and slave, and not run this as 2 separate controlled or 2 separate controllers for 2 separate pairs of IDE devices. I'm just going to run one master slave. And for now, all I'm running is a single master. So just this connection down here. And I'll have to finish out this one up here. But I kind of changed how I brought in logic as far as this chip select or cable select, whichever it is. And then this one across from it, pin 38. For now, I'm using this A2. And what I'm kind of learning is that those 2 select lines are mutually exclusive. I'm not seeing any use cases where both of them will be active. So they're active lows, and I'm not finding any cases where they're both going to be active low. So I might change my logic around a little bit. I can cut down the IO space if I trim this down by taking out an address line, because I don't need to go through A1 through 5, I can just go A1 through 4. And these pairs, I'll just invert one of the signals, like A1 here, and an inverted A1 over here. And that logic is coming from down here, but I'll just have another set that uses an inverted A1. And that way I can flip between CS1 or CS3. Now what those are used for is really to select which register sets I'm working with. And for the most part, there's one register set that's going to get used, and maybe a secondary register set, an alternate, I think it's referred to, that maybe I'll do something with in the future, but so far I'm not needing to use it. So as I've built this out, this is what it looks like, and I posted this in my community tab on my YouTube channel, but basically I'm just using this little extender off of one of my ISA slots so that I can lay this card down and probe it with my oscilloscope and things like that. And I've tested it in a slot, and it actually runs better in the slot than, as you would expect, than running down through this extension through these ribbon cables. And the front doesn't look so bad, but like I mentioned, the original schematic and what I actually have here are a bit different, and really all of that ended up, I did that on the back of this. And so I leveraged those headers just to get to the address lines I wanted, and then I changed where I ran those address lines. Or maybe I ran through the logic a little bit different as far as how I was decoding when all of this should be enabled or not. And you're going to see little cuts all over the place where I've cut signals and then ran this to really rework, backing up, reworking, going from this picture here over to this picture here. And fair amount of work, but it was fine, easy to do on this card because it was so spread out. So that's what the card looks like, and seems to be working. So as far as code, I've gone in and put in some of these just to reference where in my card I'm going to access different registers. And this up here, I'm not even using these declarations, but I'm just showing which bits. So I have data address 0, 1, and 2, and then that select line 1 and 3, or sometimes it's referred to as 0 and 1, but that's just showing which pins or basically which bits of the address are for each of those things. And then I put those together in a certain way, and the way I'm doing it is in my code here. Basically, the way I'm doing the address decoding, I have a pair of jumpers on the card that are setting this 0 and 1. So those are the first two bits set by jumpers for the addressing. And then the question is really coming into these three address lines, A0, A1, A2, which I'm running basically from my ISA bus, address 1, address 2, address 3 to get to those. And then the last bit is just basically what would be A0, so it's basically my odd or even. So those are always going to be zeros. And then right before that, a 1 and a 0 are how do I set these other two, CS1 and CS3, or first it's CS3 and then CS1. But anyways, putting all of that together, I have set up this bit pattern to be my register for data for drive 0. And then this is my next register. So register, 0, 1, 2, and I work my way up through register 7. Now some of these you'll see that are actually the same, like reg error and reg features is the same value. But when you read, you get back error data, and when you write to it, you're writing feature data. And same with status and command. Both of those are on the same IO address. But if I read from it, I get back a status. If I write to it, I'm writing a command to the IDE device. And so I just noted, are they read writes, read or write, and then what address am I using each of these at? So those are the addresses, although I'm always going to use these labels over here. And now normally, instead of being 44 hex, I think in a traditional IBM PC, this would be a 1F0, and that would work up to 1F7. And then when I get into this alternate register, you can see I flip these select bits down here, and instead of a 1-0, it's a 0-1. And normally on a traditional IBM PC, it'd be a 3F6, I believe, for that address. I'm using 42. So I don't think it really matters. These are just the addresses I'm using with my decode logic that fits within my overall address space or IO address space on my system. Then after that, I went in and I built some functions here, trying to learn how to write these. What do I need to do to actually do these different things for an IDE device? A lot of good information out there. So I've been reading a lot and learning, I guess, as I go through this, like my entire project is, of course, but this is what I have so far. And these are not fully fleshed out, but it's a good start. So I wrote a routine that will help me identify the drive, so pull back data about the drive so that I can use it properly moving forward. I have a routine that prints that out to my serial output just so I can kind of debug a little bit. I have a reset routine. I have a read routine. I can then print a buffer. So if I go out and I read, whether it's a bunch of data off the disk or I read this identification information, I can print that out to my serial either in hex or in ASCII. And then I'm starting this interrupt 13, which is disk services. So previously I've done video services or DOS services. Now I have a whole series of interrupts that I need to build out that are disk services. And so when I get into that, there'll be calls that come up to identify drive or read. I obviously will have to do a write, and there's a bunch of others that I'm going to have to work on as I go. Now, if I go out and I start with this identify drive, I can make a call and read from a register basically. And there's a specific register I read from that will return basically this information. So this is coming from a compact flash memory card manual from SanDisk. But when I go out and I ask this CF card for its drive information, it's going to come back with all of this data that I can read. And I read this and I initially just put it into essentially an array in memory. But then I take out the parts I want and store them essentially in variables that I can use in the future as I do additional I/O work with the device. And so these are some of those variables that I've set up. So I can store disk info for my drive 0, like how many cylinders does this flash card show up as. Obviously a flash card doesn't have cylinders and heads like a traditional rotational disk, but it has to somehow emulate that. And this is what it's saying, is how many cylinders, heads, and I'm basically making a spot to store that. So how many cylinders, how many heads, and this is the default. So that card is going to report what does it think it has for cylinders, heads, bytes per sector, and then there's also this current number of cylinders, current number of heads, and then there's current capacity in sectors, and that's split across 4 bytes here. So there's a high word and a low word basically. And then there's a total number of sectors addressable. Those are all things I'm pulling out because I think I'm going to use those as I move forward. And there's other things, for example, an ASCII descriptor, there's a serial number, there's other types of capacity, things in this table I can read out. But these are the ones for now I'm actually going to do something with and store them. Now, as far as CF cards, I grabbed just some cards I had lying around. I have some newer ones coming, but this is what I had sitting in my desk. And so this Kingston is probably the only quasi-modern CF card I have. And then I go down to older, like this Toshiba, or even older, this Delkin devices, all the way back to a whopping 16 meg Epson card I had for an old camera. So these are the ones I'm playing around with. And what I really want to be working out of this set is with this 8 gig one. But I'm just testing to see if the code I'm writing will also work with some of these really old cards. And I'll get a couple newer cards and see if I get similar or different results. If I start with this 8 gig card though, in my serial output, when I turn on my system, I'm logging stuff out to this serial. And this is just a quick print screen to kind of show you what that looks like. But after I'm doing my initial normal, initialization, which you've seen in a lot of my videos, like where I'm reading from the SD card and things like that, I then turn around and I read from the CF card through these IDE calls. And I first pull back the device, the drive info, and I just print it out as ASCII, and that's what you're seeing here, actually starting with the J. The Q and S are just little debug characters I put in, but J equals, and then all this down to here is basically what I'm reading off of that card for the device info. And then I show it again in hex, and this is what it looks like in hex when I read it back. But then I pull out all of those pieces, like I showed if I back up 2 slides to this. If I go to specific locations within that ASCII data, well, within the hex data here, this is really what I'm reading back then for those things. So here I can see that I have this many cylinders on this card, and so it's hex 3D B6, this many heads, bytes. And if I do the quick conversion, because I was just quickly dumping this in hex, but if I just manually do that conversion, that shows up as almost 16,000 cylinders, 16 heads, 576 bytes per sector, with a total of roughly 16 million addressable sectors. And if you take that number of sectors times the sector byte size, that comes out to an exactly 8 gigabyte even for address space. So as I'm reading the disk info from that CF card, it's reporting that I have an 8 gig card, and is showing me this geometry, I think is how it's referred to, of cylinders and heads and sector size and things like that. And then after I read that, I actually go out and read some actual data. So this down here is I just picked a random address and said, bring back some data from that card just to make sure I can bring back data. And that all seems to be working fine. I then did the same thing for the other cards, and like here's this Delkin, and you can kind of see up here, it pulls back that identifier just fine, and here's my cylinders, heads, etc. Then I did the same thing for this really old Epson, and it came back, not many heads here, so cylinders and heads, it's pretty small. And interestingly, the addressable sectors came back as 0, but if I look at capacity, the low and the high here, I can kind of get an idea of what the capacity is, if these numbers are even right. And I've not validated or calculated anything here. And then I did also the same thing with this Toshiba. And interestingly, somewhere in the data I'm pulling back, there must be something funky in a character or something that then triggers it's probably a bug on my code. And I think this is really in the SPI data. So I'm sending SPI from my 286 to a little nano, and the nano then goes over to my PC, and this print screen is coming from a terminal program on my PC. But somewhere in there, there's a character that is outside of something I'm handling properly, and you can see it messes up everything after the first character on these lines, and then for some reason the X doesn't show up right, and but it looked like it still got data here. And these all have zeros, probably because those cards are empty, so the spot where I'm trying to read from either isn't a valid spot, or likely it's just empty, there's nothing there as I get into that. So this seems to be progressing. I am able to go in, read the disk info. If I back up a slide, this is more like the card I'm going to use, and the information I'm getting back looks good. I'm storing that information. If I back up even further into these variables, because then as I get into future work of reading and writing, I'm going to need to know that information, I believe, to finish out those routines. The read routine I have right now is just starting at a spot and counting up and grabbing me a bunch of data, but that by itself isn't going to be super helpful. But I think if I back up here again to some of these previous functions over here, if I can get this read done and then I don't know if I even need more than that, just the read done, then I can work on how do I actually read out whatever I need for data to boot to the drive. So how do I get that kernel boot and load up the kernel off the CF card? And then that kernel can then load up the command.com or whatever it is that I end up using, freecom, and then start running my operating system. And then I can see what kind of interrupts I'm missing and things like that. And maybe as a side note on a couple of things, I have added interrupt handlers for all not all, but a lot of the interrupt numbers, pretty much all the way up through like hex 40 or 50, so that if at some point I get a call for an interrupt that I have not put in code for, it'll notify me and tell me which interrupt was called from my FreeDOS. Maybe one other side note, I did swap out the nano for a nano every, and I was not impressed with the nano every. I found that its SPI functionality was worse, undocumented, really not even officially supported as I got into it. Even though they listed as a master or slave capable, it's pretty flaky as a slave device. I got it to work just fine, but it doesn't run as well or as fast as the plain old Nano does. So I'm just going to leave my Nanos in place and not use the Nano every. So that's kind of a tangent. If you've been following the series, I had talked about that at some point. But so I've got my different interrupt handlers in place to catch things as I start to try to load up a kernel here. And if I can get, like I said, the rest of this read figured out, get that put into my interrupt 13 service handler for the disk, I think I'm going to be close to trying to load up an actual kernel from CF, from a CF card into memory, and see if I can actually pass control to it and make that work. I am using a lot of resources, like I mentioned earlier, and I will have a blog post that goes with this video. And these are some of the ones that are going to be in this blog post at the bottom that I'm already using and finding quite helpful. So a lot of good stuff here, and pretty interesting video out there from Queso Fuego. And I reached out to him and just asked if he would share his code. He previously had shared it, but a link wasn't valid anymore. And he got back right away and updated the link. And he's got some code out there that I can take a look at too. And there's other sample code in a lot of these pages. So a lot I'm learning as I go through this, but it seems like I'm progressing. It is super time intensive, I will say that. So this stuff, it's try something, try it again, and eventually I kind of get things dialed in as I go or learn. And part of that is me just learning some assembly. Part of it is not being super familiar with the IDE specification and all the registers and things like that. And there's a lot of nuances. It seems like so many different if you have this type of drive or that type of drive, or different situations that you really have to plan into your code to deal with. Luckily, I'm going to just support CF cards, and that's what I'm going to be doing my testing around, and make sure I can get, for example, that 8 gig CF card working consistently, which it is at this point. But that's what I'll be testing. So that's all I have for now. I will keep working on getting this read functionality working so that I can get my kernel loaded. And then we'll see if my system implodes when I try to load up a FreeDOS kernel. I imagine it will, and I'll have to identify all the different interrupts that I need to get in place yet, and I'll just keep chunking through those.